Welcome back to chemistry. We're starting a new unit today on thermochemistry and thermodynamics. In part one of our video today, we're going to look at the laws of thermodynamics and a couple of different kinds of energy, specifically potential, kinetic, internal, and we're going to look at work. What is work? Let's get started. First of all, the laws of thermodynamics. Now you can see these written in a lot of different ways, a lot of different types of verbiage, and I've kind of arranged them so that I think that they're easier to understand, although it's not exactly the same verbiage if you say went on Wikipedia. But the first law of thermodynamics says that energy of the universe is constant. Energy does not change. It can change forms, but it cannot be created or destroyed. Energy is conserved just like mass is conserved. The second law says that entropy of the universe is always increasing. So in a spontaneous reaction, entropy of the universe would be a positive value because it's increasing as we go. And we're going to get to later what entropy is. And the third law says the entropy of a perfect crystal at 0K is 0. Pretty much the only thing that has 0 entropy is a perfect crystal at absolute 0 temperature. So you can kind of rearrange that to say everything has entropy, because virtually nothing is a perfect crystal at absolute 0. So everything has entropy. We're going to be talking a whole lot more about what energy is and what entropy is, energy for this unit, and entropy in our subsequent videos. Let's start with energy. So the laws of thermodynamics are concerned with the transfer of energy, specifically that's what we're looking at here, and entropy, between the system, the surroundings, and the universe. The two types of energy we're going to be concerned with are potential energy, generally we think of that as energy in the bonds, and kinetic energy, generally we think of that as energy of motion. Let's look at that more specifically. Potential energy is a measure of energy stored in the bonds of molecules. As atoms within a molecule move closer together, potential energy decreases because the energy required to hold the bond together decreases. So, the closer they are together, the lower the potential energy. This is caused by the attractive forces between the electrons of one atom and the nucleus of the other. As atoms within a molecule separate from each other, potential energy increases because of the additional energy required to hold the atoms together, since the attractive forces between the electrons and nucleus are decreased. So we say potential energy is stored within a bond, but it's not really stored, it's just the energy that's being used to keep the bond together. The other type of energy we're concerned with here is kinetic energy, a measure of the average motion of atoms or molecules in a system. Kinetic energy is directly proportional to Kelvin temperature, and thus doubles when Kelvin temperature doubles, or halves when Kelvin temperature halves. Notice that we're talking about Kelvin temperature, not Celsius temperature. It is not directly related to Celsius, just Kelvin. Maxwell-Boltzmann distribution will actually explain that a little bit better. This shows the average kinetic energy of molecules, or how it increases as temperature increases. Notice that the distribution of kinetic energies becomes more dispersed as temperature increases. So if you have something at a relatively low temperature, in this case 250 K, the average kinetic energy of all the molecules is much lower than if you had something at 500 K, or if you had something at 1000 K. So the average kinetic energy is the highest up here at 1000 K, and the lowest down here at 250. But notice that the distribution of energies becomes more dispersed, so less particles have this particular energy at the higher temperature. The particles are more dispersed. But that's why we're talking about the average kinetic energy rather than the absolute kinetic energy. The other thing you can look at with the Maxwell-Boltzmann distribution is activation energy, and we're going to get to this more when we get to kinetics. But activation energy is the amount of energy required to get a reaction started. So let's say a reaction requires this much kinetic energy to get the reaction started. So if it requires this much kinetic energy, something at 250 K would only have this many molecules molecules that would have enough energy to actually move the reaction. If it was 500 K, we would have this many molecules to get the reaction to happen, significantly greater number. But if it was 1,000 K, now we'll have all of these molecules that have enough energy to get the reaction started. So a greater average kinetic energy will generally help you get to your activation energy quicker. But quicker is a kinetics issue, and we'll get to that in another unit. So energy transfer. Now we know that energy is conserved. It cannot be created or destroyed, but it can change forms. So when two samples of differing energy come in contact with each other, energy is transferred from one to the other. This results in a decrease of the kinetic energy of higher temperature systems and an increase in the kinetic energy of lower temperature systems. So energy always moves from the higher to the lower. Eventually the two systems will reach thermal equilibrium and then they'll be at the same temperature. So we need to know about the system versus the surroundings so we can talk about transfer between the system and the surroundings. The system is the actual chemical reaction that's taking place, the thing that you're actually interested in. The surroundings are the entire universe outside of that chemical reaction. So if your system is a reaction in a beaker, the surroundings is the beaker itself and the air around the beaker. And so then the universe is the system and the surroundings. It's pretty much everything all-encompassing. So the universe would be the reaction in the beaker and the air outside of the beaker. When we say universe here, we're not literally talking about the universe and the stars and the sky. We're talking about the things that are involved in the reaction, the system itself of the reaction and its immediate surroundings. So another energy that we'll talk about, internal energy, is actually going to deal with kinetic and potential. It's the sum of the kinetic and the potential energies of particles in a system. The formula is delta E, which is the change in internal energy, is equal to Q, which is the heat that's transferred into or out of a system, plus W, which is the work done on the system by the surroundings or on the surroundings by the system. The signs here are important. So if heat is transferred in, that's going to be a positive value of Q. And if work is done on the system, that's going to be a positive value of W. If heat is transferred out, that'll be a negative value. It's losing heat. If it's done on the surroundings by the system, it's a negative value because the system is losing heat towards the surroundings. Work is associated with the expansion or contraction of gases. And so in a minute, we're going to talk about how gases will create or require work. So we just said that work is associated with changes in the volume of gas. So specifically, the formula for that is negative P is the external pressure times delta V, which is the change in volume. So if you had an endothermic system, and in your pictures, this is the one on the left at the bottom, the pressure exerted by the gas particles in the surroundings is greater than the pressure exerted by the particles within the system. So these particles are essentially putting way more pressure down, and these particles are putting much less pressure up. This results in an energy transfer from the surroundings to the system. According to the above equation, work is going to be positive because the volume of the system decreases throughout the reaction. Work is positive because energy is going into the system from the surroundings. Work is positive because negative pressure times a change in volume. The change in volume will be negative, so you'll get a positive value for work. In an exothermic system, this picture is on the bottom on the right-hand side, the pressure exerted by the gas particles in the system here is much greater than the pressure exerted by the gas particles in the surrounding. This is going to be much less. This results in an energy transfer from the system to the surroundings. According to the above equation, work is negative because the volume of the system increases throughout the reaction. So, since energy is essentially, let's make that red, essentially leaving the reaction, then work is negative. Or if you're looking at this formula, negative pressure times delta V, and delta V itself is positive, because it's increasing in volume, then this will get you a negative value for work. Let's work a couple of examples. A gas expands from 0.87 liters to 2.46 liters in a cylinder under constant external pressure of 1.05 atmospheres. Calculate the work associated with the expansion of the gas. So the gas is expanding, which means essentially the gas is putting way more pressure on the surroundings than the surroundings are putting on it. So let's hypothesize, should work here be negative or positive? Since the energy is going out towards the surroundings, work should be negative. Let's just keep that in mind when we try to solve the problem. So their formula here, work is equal to negative P delta V. So delta V is the change in volume. Let's math that out real fast. 2.46 liters minus 0.87 liters is 9, 5, and a 2.59 liters. So that's the change in volume. And the pressure is 1.05 atmospheres, so we're just going to plug that in here. So that's just going to be 1.05 times 2.59 and make that a negative value. And I ended up with negative 1.67 liters times atmospheres, which is a really odd unit, liters times atmospheres. That's not something that we're normally associating with in chemistry, although you do know liters and atmospheres. But I think it's more helpful here to think about joules. So 1 liter times atmospheres is equal to 101.3 joules. So we're actually going to convert that to joules so that it comes out in a unit that makes more sense. 1 liter times atmospheres is equal to 101.3 joules. Let's just factor label that. I end up with negative 169 joules. Hey, it's a negative value, and we said it was supposed to be a negative value. Awesome. Let's try another example. 1142 joules of heat are added to a cylinder, which causes the contained gas to expand from 1.35 liters to 4.18 liters under a constant external pressure of 1.03 atmospheres. Calculate the delta E. So the gas is expanding. It's giving energy to its surroundings from the system, so the work should be negative. But heat is added. So the heat itself, because it's going into the system, heat should be positive. So we're just going to keep that in mind, what it all means. If heat's added to the cylinder, it's coming in, so it's positive. If work is being done on the surroundings, it's going out, so it's negative. So we'll just keep those in mind for a moment. Let's look at work first. Work is going to be equal to negative P delta V. Delta V is 4.18 liters minus 1.35 liters equals 38.2. Okay, so this is going to be negative 1.03 atmospheres times 2.83 liters. And if we multiply that through, we end up with negative 2.91 liters times atmospheres, which is an awkward unit, and it doesn't match the joules from Q. So 1 liters times atmospheres is equal to 101.3 joules. Factor label that, and you end up with negative 295 joules. But the question here is not asking for work, it's asking for delta E. And delta E, if you remember, is equal to Q plus W. Q is the heat gained or lost. W is the work done on or taken in by the system. So Q, we said earlier, is going to be positive because heat's added. So this is positive 1142 joules plus Work is negative because that work is done on the surroundings. So plus negative 295 joules. So positive 1142 plus negative 295 gives me positive 847 joules. And that's my my delta E for this process. So overall, the energy is added to the system, even though some work is done on the surroundings by the gas expanding. Okay, that's all we have for these different types of energy. We'll see you next time for delta H.